Alright, so in class we got through all of really the new notes, and all that's left is another example sort of tying all the different things we learn in this set of notes together. So really, you should be able to do this entire example without even having to watch the video, and I actually would strongly recommend that you actually just pause the video here, work the entire problem, and then kind of come back and see if your answers match mine. And then of course come back to see if the stat crunch part is making sense as well. So, hopefully now you've already worked the problem. And so first, by just reading through the problem, we're trying to estimate the proportion of items that are defective. So we're taking a systematic sample of 1,500 items. So that's going to be our N. And we found that 45 of them are defective. So our P hat will be a 45 out of 1,500, which is just 0.03. And hopefully it actually makes sense this is a small number. Our goal is to estimate what percentage of the items are defective. We probably really hope that that percentage is a small number and we don't have a ton of defective items that we're working with here. Now in part A, we're asked to do this with 99% confidence, and we will also verify this in StatCrunch. So our first step when doing a confidence interval is to define our parameter, which here is our P, and defining what P actually is here in words. So P, since it's a parameter, is a population proportion. And here it's that proportion of defective items on this assembly line. Our second step is to do our conditions. So we need to have our relatively random and unbiased sample. As it states here, they took a systematic sample of 1,500 items. That means they maybe pulled this first item, then the next 100th item, then the next 100th item. So kind of one every now and then, it's just coming off of their assembly line. So hopefully it seems like this systematic sample would be a smart way to do it, because they're not necessarily getting them all right after each other when there might have been a malfunction with the machine. So there really isn't any known bias here going on with our sampling method. Then we need to check to see if N times P hat is at least 10. So our N is just 1,500. Our P hat is 0.03. So we get 45 back, which again, notice that's actually the number of defective items in the sample. That's just what NP hat actually is. Then our N times 1 minus P hat, we can do the math to it pretty easy, but that's just going to tell us then how many items were not defective in our sample. So we get 1455, which is at least 10. Sorry, I couldn't quite fit it there for us. Alright, step 3 is doing the actual formula. So the first thing we need to do is find our Z, and this is a little refresher on finding our Z. This is finally where that confidence is being used. This is where that 99% is being used. So there's 0.99 in the middle. That leftover 1% split up into 0.5% on either side. Our goal is to find that number. So we're going to the table looking for everything to the left of that question mark, which is 0.9950. This is where we're working backwards in the table. The closest thing we find to that is 0.9951, giving us a Z of 2.58. Now we can plug all of that into our formula. So we take our P hat minus our Z times the square root of P hat times 1 minus P hat over N. And then it's the same thing on the other side except for just a plus. So 0.03 plus 2.58 times the square root of P hat times 1 minus p hat over n. And then again, like on a test or a quiz, you just need to show me the starting formula and then the numbers that you get. But the more work you show in between will allow me to know if a number does go wrong, possibly where it went wrong. So the first thing I want to do is actually do my square root part. So I'm going to keep that 0.03 and that 2.58. Once I find that square root, it should be about 0.004405. This is a reminder, that's what's called the standard error. And notice it's the same formula on the other side with just that plus sign, so I really don't need to do that calculation again. Now we can actually do our multiplying. So we're going to take our 2.58 times that standard error, and we get 0.0114. And then again, a reminder of what this number is. That's what our margin of error is. Then finally we can do our subtraction and addition. We get 0.0186, 0.0414. And then I can change this to percentages, so multiply by 100%. That's 1.86% to 4.14%. And then last, we just interpret that number, that interval. So we are going to say that we are 99% confident that between 1.86% and 4.14% of items on this assembly line are defective. So that's our confidence interval. Now let's verify that in StatCrunch. So we just pull up StatCrunch. We don't need to enter any data or anything. We're just going to open it. We go to our stat, proportions, one sample with summary. We put in how many defective items there were and how many total items there were. Basically, those are our two numbers that create our p hat. We say we're doing a confidence interval, but we're doing a 99% confidence interval, so I need to change my level to be then 0.99. Then at that point, we hit our compute, and so we get some numbers here. So again, the sample proportion, that's our value of p hat that we created. The standard error was this square root part that we calculated, this 0.0044 number. So you notice how that matches. We get then the lower limit and the upper limit as well. And these are our two endpoints. So we had 1.86%, so that's pretty darn close to what we have here. And 0.0414, pretty close to what we have there. So it's a nice way of double checking that you've done your math correctly as well. So that's just part A of the question. Then it asks us, so could we conclude that the proportion of defective items is less than 4%? Why or why not? So if we look at our confidence interval, we're really asking ourselves, is the entire confidence interval less than 4%? It's not, right? So part of our confidence interval is greater than 4%. So we cannot conclude that because of that reason. So the entire confidence interval is not less than 4%. So even just part of it is bigger, I can't say that it's less than 4%, because I'm not any more confident than any number in that interval than any other. Finally, we want to see that the assembly line to figure out how many items they would need to sample to be within 0.5% with 95% confidence. So we're trying to figure out how many items we need to sample. So that's sort of a hint that we're trying to find sample size. My formula for that looks like this. So I need to have a z, I need to have a margin of error, I need to have a p hat. So margin of error is how close we need to be. And in decimal form, so I'm going to divide that 0.5% by 100, so that's going to be 0.005. Z is based upon our confidence level. So let's find our z. So this time 97% is put in the middle. So that means 1.5% is put on either side. We're going to go to the table looking for everything to the left of that question mark, which this time is 0.9850. We're going to go to the table looking for that. So 0.9850. We do actually find it perfectly here. So this time our z is going to be 2.17. So we now have our z, we have our margin of error. The last thing I need to know is p hat. Well, we're still doing it based upon what we have here, so we do actually have a p hat that we can use from our previous similar study. So right last time that we did this, they found p hat to be 3% or 0.03. So I have all of those numbers that I can plug in. So n will need to be at least as big as our z over our margin of error, all squared, times p hat times 1 minus p hat. And that should give us 5,481.2. Remember, it's got to be a whole number here. We always round up. So we're going to do 5,482 items. So we need to sample at least 5,482 items. Now, as a little note, if we wouldn't have used a p hat of 0.3, if your p hat would have been 0.5 instead, which is what we use when we don't have anything else, what would we have got? Then you would have found that you needed to sample over 47,000 items. So as you can see, if you have a p hat to use, that you have an idea of what that is, it can have a huge impact. So a little over 5,400 items compared to 47,000 items. Right, that's more than 8 times more than what we have up here. So just by knowing that we don't have a ton of defectives, that helped us reduce our sample size immensely. So hopefully you got all of the right answers and you're feeling good for class tomorrow.